Yes, sir.
Okay, great. Hopefully you can see my screen.
Yes, sir.
Okay. Okay, so in the last class, we had a nice discussion about capacity and mutual information. We saw that the capacity of a channel is equal to the maximum of the mutual information between the input and the output of the channel, where this maximization is taken over all possible input distributions. So given any, so note that the channel is completely described by the transition probabilities Py given X, and for every choice of Px, we get an achievable rate. So the mutual information is always a rate which is asymptotically achievable with vanishingly small probability of error. But the maximum over the mutual information gives you the maximum possible rate at which you can transmit across that channel. We also saw the relationship between the mutual information and the entropy. So the mutual information Ixy is equal to h of x minus h of x given y. But the mutual information is also symmetric. So I of xy equal to I of yx. And this is also equal to h of y minus h of y given x. Right? So as we discussed in the previous class, this has the following interpretation, that the total amount of uncertainty in the transmission is equal to h of x. So every channel use, there's an uncertainty of h of x bits per channel use about the input. After observing y, this uncertainty is reduced. So h of x given y is the residual uncertainty in x given y. And the amount of information that you get about x having observed y is equal to the difference in the uncertainty about x minus the uncertainty that is still left over after observing y. So that's the amount of useful information you can get about x from y. And that is also operationally true in the sense that you can design a channel code such that you can operate at a rate I of xy and still achieve a vanishingly small probability of it. We also saw the following chain rule for entropy. So if you have two random variables x and y which are jointly distributed according to some distribution pxy, then the joint entropy of xy is equal to the entropy of x plus the entropy of y given x, and it's also equal to the entropy of y plus the entropy of x given y. So the total uncertainty about the pair xy is equal to the uncertainty of one of these random variables plus the amount of uncertainty left over in the other random variable having observed the first one. Right? Any questions till now?
Hello, sir.
Yes.
Sir, I'm sure you already mentioned it, but in all of our discussions, we talked that as n tends to infinity, right?
True.
So what does it actually mean? Because none of our whole languages actually have whatever we send is gonna need infinite bits, right?
True. So that's a valid point. So when I say that we're dealing with n tending to infinity, it means that so firstly, we want a result. So we're looking for mathematically interesting results at this point, or more, or to put it in a slightly different way, we want something that we can handle easily. Right? So an equally valid and an equally important question is the maximum rate. Let's talk about the channel coding problem. So what is the maximum rate at which you can communicate for a given channel py given x and for a given block length n and a given probability of error epsilon. Right? So that is really the quantity that we're interested in. Now what happens in practice? In practice, if you look at, say, voice communication or standard data communication, you basically communicate in blocks. So you basically transmit a frame of roughly 10 to the 5 to 10 to the 6 bits. Right? So what is 10 to the 6 bits? It's roughly 1 megabyte, right? So and the data rates that one is typically interested in is several. So maybe a few megabytes per second if you're talking about like 4G type of communication. So you're interested in 10 to the 5 to 10 to the 6 megabytes per second. Sorry, 10 to the 5 to 10 to the 6 bits per second. And for many of these applications, a latency of a fraction of a second is fine. So indeed, this is the block length. This is the value of n that one is typically interested in for data and voice communication. Right? And what kind of probability of error are we interested in? For voice communication, the probability of error that we are interested in is around 10 to the minus 4 or so. Right? So it's as though that epsilon is really, really small and n is really, really large. And in this case, the capacity, or letting n to tend to infinity and epsilon to tend to 0, turns out to be good enough for our application. Right? And it's also so one of the main reasons why people study limits like n tending to infinity and probability of error tending to 0 is because this is easier to analyze. It's easier to get a nice expression. We've seen that the maximum rate of communication is equal to I of xy, which is something clean and something that we can very easily analyze. Now, people have also studied the second object, this quantity over here. So for a given n and a given epsilon, what is the maximum rate at which you can communicate? And it's not a very clean thing. You can't obtain a closed form expression, but you can still numerically evaluate this and obtain the maximum possible achievable rates of communication. Okay, and but these results are very, very recent. They came out maybe just 5 6 years ago, perhaps. So a lot of this is still relatively new, and there are a fair bit of open problems in this area. Unlike the problem of traditional capacity, where you are interested in the regime of large block lengths. Again, as I said, for traditional wireless communication, this regime seems to be good enough. One can approach very close to capacity. But there are certain applications where this is not good enough. So when you have very strict latency requirements, or you want the probability of error to be really small, or in some applications, it's okay to have the probability of error to be reasonably large. These assumptions don't go through, and it turns out that the rate is in fact far less than the mutual information. But that is, of course, a separate problem, and we won't really address that in this course.
Thank you.
Any other questions? Okay, so far we've seen two quantities, information theoretic quantities. One was the entropy, the other is the mutual information. So now I'll define a third quantity, which I call the relative entropy, or the Kullback-Leibler divergence. So suppose that we have two PMFs, PX and QX, which could be arbitrarily chosen. So both of them are defined over a given alphabet script X, and they can be arbitrary, but the only property that they need to satisfy is that P of X should be equal to 0 if q of x equal to 0. So if for some symbol x, q of x is equal to 0, then p of x should also be equal to 0. That's it's only for distributions of this form that we define the Kullback-Leibler divergence, or at least we define it in this particular form. So the KL divergence, or the Kullback-Leibler divergence, between px and qx is given by this following quantity. So it's the sum over all x of p of x log p of x by q of x. Okay, and so this is true as long as p of x equal to 0 if for all x such that q of x is equal to 0. If p of x is equal to 0 for some x such that q of x equal to 0, then we define the KL divergence to be infinite. So sorry, if there is an x such that q of x equal to 0 and p of x is not equal to 0, then we define the KL divergence to be infinite. Okay, so because technically log 1 over 0 is not defined, so we define the KL divergence to be infinite if q of x equal to 0 and p of x is not equal to 0. Okay, and similarly, if we have two distributions, or if you have distributions over two random variables, so we're given a px, a py given x, and qy given x. So we have two conditional distributions py given x and qy given x, and a distribution px. Then the KL divergence between py given x and qy given x is defined in this particular fashion. So it's the sum over all possible xy of pxy of xy log py given x divided by q of y given x. Okay, so it's a definition, and in just a moment we'll see the operational meaning of the Kullback-Leibler divergence and how it arises as another fundamental limit in a different problem. Okay, but before we go to that, let us consider the following problem. So suppose that we have a joint distribution pxy. Can you tell me what the KL divergence between the joint distribution pxy and the product of the marginals px py is equal to? Is this something that you've already seen?
Mutual information.
Exactly. So it's equal to the mutual information, right? So what is this KL divergence equal to? This is equal to, again, let's go by this definition over here. This is the sum over all possible xy of p of xy log p of xy divided by the product of the marginals. So this is p of x, p of y, right? And this is precisely the mutual information between x and y. Right? So immediately we've seen a relationship between the KL divergence and the mutual information of two random variables. So for a specific choice of P and Q, you get the mutual information between X and Y. Right? So, but really, what is the operational meaning of the KL divergence, and where does this arise in practice? So recall that in the very first class, I talked about three main problems that we're interested in. The first problem was how do we compress data efficiently? And for that, we saw that the minimum rate of compression is equal to the entropy. Then the second problem was, how do you communicate reliably across a noisy channel? And for this, we saw that the mutual information gives an achievable rate. The third problem that I talked about was like a problem of what is called detection, or in some sense classification. It's not classification so it's slightly different from the classification problem studied in the CS literature. So let me define the problem. So the problem is the following. Broadly speaking, the problem is the following. You're given, say, emails, and you want to classify them as spam or not spam. Okay, and the way we will model this problem is the following. So we have a sequence x1 through xn. Right. So think of this as a single email. The email has maybe n letters. Okay. And again, we will use a very simplistic assumption that x1 through xn is IID distributed according to some px. Okay. Again, this is not reasonable for standard email, but these ideas can be extended to arbitrary distributions. So that's fine. Now px, depending on whether this is spam or not spam, the distribution of the email could be different. The statistics of the email are going to vary depending on whether the email is spam or it is a good email. It's not a spam email. So I'll say that x1 through xn is distributed according to ps if it is really a spam email, and it's distributed according to PG if it's a good email. It's not a spam email. Right? So PS is the spam distribution and PG is the good distribution. And one way to think about this is that so if it's a spam email, then maybe certain words occur more frequently. If it's a good email, then those words don't occur very frequently. So for example, in a spam email, you may have words such as money or account or something of that sort occurring very frequently. Whereas in a good email, say if it's an academic, if you're designing a spam filter for an academic or a student, then words of that sort don't occur that often. Okay, and so in the problem we'll assume that these distributions, the spam distribution and the good distribution, is already known to us. So maybe we have a large repository of spam emails and good emails, and we estimate the distributions of the spam email and the good email a priori. Okay, so given these distributions and given a new email, our goal is to classify this as spam or not spam. So your input, so this is known to you a priori, and given this, you have to design an algorithm such that given any input xn, you have to output spam or not spam. So spam or good email. Okay, so if you declare this as a spam, then it goes into the spam folder. Otherwise, it just comes into your inbox. Right. Now, so this is the problem broadly, but we also want a measure of performance of our classifier, of our spam filter. Right. So there are different measures that one can use, and the one that I will use over here is the following. So we call that there are two kinds of errors that could happen. That is, the actual email is actually good, but then by mistake it gets sent to your spam folder, right? Or it's truly a spam email, but then it is sent to your inbox, correct? So so we have two different errors over here, and ideally we would want to make both as small as possible, but that's not always possible. So suppose that I were interested in minimizing only one. Suppose that I don't care about this particular probability and I want this probability to be as small as possible. I want the probability that I declare a good email given that, so I want the probability that I send something to the inbox given that it is spam. So this probability should be as small as possible. Can you think of one particular solution? Can I make this 0? So this probability is P1. Can I make the probability of 1 to be equal to 0?
Declare everything as good.
Sorry, can you repeat?
I'm sorry, you're subjecting the second condition also, or you're just asking can we make the first one zero?
No, I just want the first one to be 0. I want the probability that I wrongly declare something to be good, given that it is a spam email, to be 0. Can I make that?
Yeah.
Can I do that? How?
Classify everything as spam.
Exactly. So if I classify everything as spam, no matter what email I get, I just throw it into the spam inbox, then clearly the first probability is 0, but it's a useless spam filter, right? And similarly, if I want only the second one to be small, if I want the probability of declaring it as a spam, given that it's a good email, if I want this to be 0, then I just send everything to the inbox. I don't classify anything as spam. So this probability is 0, but unfortunately both these filters are not good because they don't really serve any purpose, right? So this problem, broadly speaking, is also called the detection problem, and was originally studied in the context of radar. So for example, you have a radar and you're trying to track and you want to know whether there is an enemy approaching you or not. So it's basically, it's kind of a detection. So that is why it's called a detection problem. You want to detect whether there is an enemy or not, right? And again, there are two types of errors: a probability of a false positive or a probability of a false negative. You falsely say that there is an enemy when there is no enemy, or you declare it as a false negative. You say that there is no enemy given that there is actually an enemy. Right? And you will study this in the course in the 1 credit course on detection theory, which will be offered in the next 2 segments. So I won't get into this in detail, but at least for the purpose of this course, I'll say that there is an optimal test. So subject to this constraint, you can indeed minimize this particular probability, and the optimal test, which minimizes the first probability given that the second probability should be less than or equal to epsilon, is sort of this thresholding rule. So basically the most logical thing to do would be to say that if the probability, if ps of xn is greater than or equal to some beta times pg of xn, if the probability under the spam distribution is greater than or equal to some constant times the probability under the good distribution, then you declare this as spam, right? If not, then you declare it as a good email, right? So that's the most natural test that one could come up with. And the only thing is, how do you choose this constant beta over here? And this constant can be chosen so that the probability, basically you choose this constant so that the second probability, the probability that you declare the spam given that it is actually a good email, this is equal to epsilon, right? And if you do this, then the performance, then the probability of error of the first event, it turns out, so for every epsilon, no matter how you choose epsilon, the first probability actually decays exponentially in n, and this exponent turns out to be equal to the KL divergence between PS and PG. So the KL divergence turns out to be the error exponent for classification. So the maximum possible error exponent that you can achieve for, so note that if this exponent is large, then the probability of error is small because of this negative sign over here. So the largest possible exponent that you can achieve turns out to be equal to the KL divergence between the two distributions. Okay. Any questions?
Sir,
Yes.
given one of the errors, can we predict how will the other error be?
So that is what we're doing, right? So given that the first type of error, or the probability of the first type of error is less than or equal to epsilon, we want to minimize the first type of error.
I mean to say in a direct relation, sir, not like a bound.
So basically what this says is that the minimum probability of error is exactly equal to this, given that the first error is equal to epsilon.
Okay. Yes, sir.
So, and the reason why that happens is because since you're allowed to note that there is sort of an inverse relationship between the first error and the second error, right? That's intuitively that you can see that, right?
Yes, sir.
Correct. So the larger the first, so the larger the second error you have, the smaller you can make the first type of error, right? So the more you can tolerate the second type of error, the smaller you can make the first type of error. So since you only have a bound of epsilon on the second type of error, it in fact is easier if you just take the second error to be equal to epsilon. And if you want to make this smaller, then this probability turns out to be a little larger. Okay, but once again, we're really interested in sort of the first order performance of either these compressors or channel codes or classification detection algorithms, because note that there are many other little terms over here. So there is a little o of one term. So there's some term over here which tends to zero as n tends to infinity, and this will depend on epsilon and how you choose the second error and so on. But right now, all we are interested in is in the first order error exponent, and the minimum of that turns out to be equal to the KL divergence. Just as in the case of compression or channel coding, we were only interested in the rate, right? Not really so the rate was defined to be k over n, and we're interested in the limit of k over n as n tends to infinity. So this is, but then for small n, for finite n, this behaves slightly differently, right? So this k over n, where the best possible k over n that you can achieve, say for compression, turns out to be h of x plus some other function which depends on n px. But then this quantity, as n tends to infinity, this quantity will tend to 0. But for small n, it is significant.
Sir,
Yes.
I have one doubt.
Yes.
Actually, this alpha we are choosing in such a way that it should.
Correct. So we're choosing such that the second type of error, type 2 error, is less than or equal to epsilon.
So how do we actually choose this alpha, sir, in practically?
Okay, so in practice, again, you typically would have estimated uh, Px and Ps. Sorry, you would have estimated Ps and Pg, right? So, so this probability is basically the sum overall possible xn of, so this is the sum overall xn such that the log Ps of xn by Pg of xn greater than alpha. So this is less than or equal to this is not spam, so Pg of xn. So this quantity is equal to epsilon. And one way to do this, again, it's not an efficient way, but then you list all the xn's satisfying this property. So you look at all possible xn's satisfying this property, and you list them in decreasing order of probability, decreasing order of PG probability, and then you choose the top few such that their sum is equal to epsilon. Right? So of course, so that is one approach to do it. If n is small, you could possibly do that. But again, it is not a very inefficient way to do it. And in practice, of course, you use completely different classifiers, right? You use what, a neural network or something of that sort to approximate all of this.
Fine, sir. But actually, in communication system, I guess we are also choosing this threshold somewhere, like using bit error probability. So here, sir, what we are doing actually, sir. Uh,
So again, this doesn't really arise in the problem of communications, right? Uh, so in detection, you typically, so sometimes what you do is, uh, so of course, one way to do this is to try to evaluate these, right, and then choose a threshold appropriately. The other thing is to, of course, run a large number of simulations, see for which value of the threshold you get a reasonable probability of error, and then you just choose that particular threshold.
okay, sir.
Right? Any other questions? Okay, so this is maybe a good time for a short quiz. I've sent the link in the chat box. So you can take maybe 4 to 5 minutes to solve this.
sir.
Yes, please.
Can you please post it on Piazza as well?
You're not able to access this here?
No, not.
Okay. So are you not in the team? I mean, MS Teams?
I don't. No, I'm not.
044. So what do you do for the previous quizzes?
Sir, previous quizzes were posted on Piazza.
I guess the last couple of quizzes weren't, right?
No, I think they were.
So you can take maybe one more minute. Okay, so is there anyone who hasn't filled in yet? Is there anyone who hasn't filled in? Okay, so let's continue. Yeah, you should get your scores by email. So in the quiz, what is the entropy of y given x?
Zero.
So it's 0 bits, right? Because y is a deterministic function of x. It's just the complement. So it just turns out to be 0 irrespective of what the input distribution is. Okay, so let's continue. We were discussing the KL divergence between two distributions. So in some sense, the KL divergence between two distributions measures how close the distributions are to each other or not. Note that if you have, so recall that the KL divergence is equal to the sum overall x of p of x log p of x by q of x. So from a very first look at this quantity, so log p of x by q of x in some sense is large if p of x and q of x are very different from each other. So what happens if p of x is equal to q of x? What is the KL divergence equal to? So
Zero.
if the two distributions, so if the two distributions are the same, if p is equal to q, then the KL divergence is just equal to 0.
Sir, a doubt.
Yes, please.
In the note you wrote the divergence for PS and PG,
Uh-huh.
we had a condition that PS and PS should be 0 and PG is 0, right?
Correct.
But it doesn't mean anything like it's spam. If it's what is it? PG is 0, it means it's not good.
Uh, could you please repeat?
Uh, what exactly is PG, sir?
So PG is the distribution of X if it is a good email, right? So okay, so what happens? So you have an email, right? So if it is a good email, let's say that someone decides to send you a good email, then what you observe is a sequence x1, x2 up to xn, where each xi is distributed according to the good distribution, right? If someone decides to send you a spam email, then they send you another sequence x2 up to xn, where which we assume is IID, but is now distributed according to the spam distribution. So maybe certain words occur more frequently in the spam distribution, whereas some other words occur more frequently in the good distribution.
Sir, this definition
Yes,
of divergence, we have
correct.
already mentioned that PS is equal to 0 and PG is equal to 0, no, sir?
Okay,
So it doesn't really give a meaning correctly, no, sir. PG is 0
why
means it's
not?
PS1.
If PG is 0,
It's not
uh,
good.
so not really, right? Why? Why do you say that?
Like if it's not good, it's mostly spam.
Sorry. So all we demand is that So as long as, so PS of 0, let's say, so we defined it. So for every x, so if there is an x such that Pg of x equal to 0, then it must be the case that PS of x is equal to 0. Okay, but then if Pg of x is greater than 0, then there's no constraint on PS of x. So PFS of x could be equal to 0, it could be non-zero, it could be between 0 and 1, all of that is fine.
How did you write PG of x equal to 0 implies PS of x equal to 0?
So that is a condition on PG and PS that I'm imposing. So that is what this statement over here means. So if q of x equal to 0, then p of x equal to 0. If q of x is not equal to 0, then there's no restriction on px.
So it implies
So,
that when
so basically
PS and
all I'm saying is that the support of p is basically a subset of the support of q.
okay, sir.
That is the only restriction that I'm imposing. If that is not the case, then the KL divergence is defined to be infinity.
Yes, sir.
Does that make sense? Right. Any other questions? So, so yeah, if it gets too complicated, just assume that the only restriction that I'm imposing is that P and Q have the same support. So P of X is both P of X and Q of X are, if P of X and Q of X are greater than 0 for all X, then the KL divergence is just defined to be equal to this. Okay? So this really is in some sense a technical restriction. So this is for only this condition. But if this condition is not satisfied, if there is some x, if the support of q is in fact smaller than the support of p, then the KL divergence is defined to be infinity. Okay. And maybe a good way to see why this is the case and what it has to do with spam classification, or in fact classification of any form. Consider the following case. So let us suppose that so the sequence is binary. So xi is takes values either 0 or 1. You observe a sequence x1, x2 up to xn. Okay, and let's say that PS is, say, Bernoulli P. Okay, it's Bernoulli P for some P between 0 and 1. And PG, it's a dumb distribution, but it's always, it's, say, Bernoulli 1. So it's always the all one sequence. Okay. So in this case, what is the KL divergence equal to? So PS is Bernoulli P, PG is Bernoulli 1.
Infinite.
Yeah. So it's infinite, right? And what does it say about the classification problem? It means that the probability that you declare it as a good email, given that it is not a spam email, is in fact, at least in the limit, is equal to 0, right? So it's very easy to classify something as good given that it is not spam. So if this were the case, then what would your spam classifier be?
Always good.
Are you sure? That's not a good idea, right?
Sir, can you please repeat the last statement?
Okay.
What?
So these are the two distributions. If it is a spam, if it is a if it is a bad sequence, if it's a spam sequence, then you observe Bernoulli P. If it is actually a good sequence, you observe Bernoulli 1. Okay, you observe a sequence of length n of Bernoulli 1, and so ultimately what you see is a sequence of bits, right? X1, X2 up to Xn. You don't know whether it has come from the distribution PS or the distribution PG, and your goal is to say which distribution it came from, right? So if you wanted to distinguish between a Bernoulli P and a Bernoulli 1 sequence, then what would be your test?
So, so for that we need to change this PG because it's so certain Bernoulli one.
Correct?
In this case, it's certain, sir.
That is, if it came from the good sequence. So if it came from PG, right? But you don't know whether the sequence that you have seen comes from PG or PS. So okay, let me put it in a slightly different way. So you have two coins, okay? You have two coins. Uh, one is maybe a fair coin, right? Probability of head is half, and the other is uh, say a biased coin. So probability of head is equal to 1. Okay, so both sides are basically a head. Okay, so there are one of these two coins. Okay, so there are two coins in a bag. You don't know which, and someone just picks up one coin from the bag. Okay, you don't get to see the coin itself, but you can toss it any number of times, and someone is going to tell you what the sequence is. Okay, so someone picks up one coin from this bag, one of these two coins, and then tosses it n times, and then puts the coin back into the bag. And you know what came up after those n tosses. Okay, and now your goal is to say which coin was picked, whether it was coin 1 or coin 2. Okay, is the problem clear?
So even if there is one tail, we can say it is from the probability half Bernoulli, and if
Exactly.
it's always heads, there's a chance that one of these two could come. One with
Correct.
probability one half and other with
Correct.
half.
Correct. Correct. So basically, your the a test that you could do is that you keep tossing n times. If all the n tosses are heads, then you declare it as coin 2. If if all the tosses are tails, then you declare it as coin 1. If even if one is a tail, then you declare it as coin 1. If there are no tails at all, if all of them are heads, then you declare it as coin 2, right? And in some sense, uh, this problem is sort of asymmetric, right? So if out of n tosses you observe even one tail, then you're perfectly sure that it has to be coin 1. right? It cannot be coin 2. Do you agree? So I pick up one of these two coins, I toss it n times, and out of those n times, even if I get one tail, then it has to be coin 1, that is the red coin, right? If all of them are heads, then can I say for sure that it is coin 2?
There's a chance it could be coin 1 also.
Exactly. So there is still so if n is large, then there is even at least a small chance, there is a small probability that coin 1 would have been chosen. Right? But even if there is one tail, then you're sure that it has to be coin 1. It cannot be coin 2. So in some sense, there is an asymmetry in this problem. Right? Given these two distributions, uh, there is an asymmetry in the sense that if one particular, it's easy to distinguish whether one particular event has occurred given that the other particular event has not occurred. So if you choose coin 1, then and you observe a tail, then you can much more easily say that it was in fact coin 1. But if coin 2 was chosen, if coin 2 was actually chosen, then it is actually slightly harder to say whether it was coin 2 which was chosen or coin 1 which was chosen, because there's still a small probability that coin 1 was actually chosen. Correct? And that is seen by this asymmetry in the KL divergence. Right? So So in one case, if you look at PS and PG, so maybe I should have interchanged it, but in this particular case, uh, dps PG would be equal to 0. So if PS is Bernoulli P and PG were Bernoulli 1, then dps PG is infinity. But what is dPG PS? So what is this equal to? This is not infinity, right? So it's going to be something finite. Okay, so this is less than infinity. So firstly, it's asymmetric, and it also tells you that one of these problems is harder than the other. Right? Any questions? So we'll end the class for the day, but I'm happy to take any questions if anyone has any.
Hello, sir.
Yes.
Yes, sir. What is the difference between the conditional entropy and the mutual information? Because both the term give information of one variable depending upon the another variable.
Okay, so it's just slightly different, right? So the conditional entropy of y given x, right? So this is the uncertainty in y, the uncertainty that is remaining in y after seeing x. Okay, or maybe just to keep notation a little more consistent, let me say h of x given y is the amount of randomness that is still left in x after seeing y, correct? Whereas the mutual information is the amount of information that you get about x after seeing y. So in some sense, these two are inversely related. So if you get more information about x after seeing y, then it must mean that there is less randomness left over in x after seeing y. Correct? So let's take an example. Suppose that y is equal to x. Okay. So in this case, what is the conditional entropy is? So what is the conditional entropy equal to?
Zero, sir.
Correct. So this is equal to 0, right? So there is no uncertainty left over in x having seen y because y is equal to x. Correct. So, but what is the mutual information equal to?
Sir, as per formula, it should be P of X, but entropy of X, but I didn't understand how.
So just use, say, evaluate I of xy just using the exact formula P of xy log P of xy divided by P of x P of y, right? So x is equal to y. So this is actually some more all x. P of x log P of x, which is actually equal to just P of x P of x. Right? So this is equal to, correct?
Yes, sir.
Right? But what is this equal to?
This is entropy of X.
This is entropy of x, right? So if y is equal to x, then the mutual information is equal to the entropy, whereas the conditional entropy is equal to 0. So the larger the mutual information is for a given distribution px, the smaller the conditional entropy should be, and the larger the conditional entropy is, the larger the mutual information should be. And that is easily seen from this relation h of x minus h of x given y, right? So the larger h of xy is, the smaller I of xy. If h of xy is small, then I of xy is large, right?
Sir, if X and Y are independent, then
Correct.
information, this I term will be zero, right?
Exactly. So if x and y are independent, then the mutual information is equal to 0. But what is the conditional entropy equal to?
In this case, H of X.
Correct. So but try to also do this, evaluate it using the expression. So what is, if x and y are independent, then what is pxy equal to?
Px into Py.
Correct, right? So px py log pxy, which is px py divided by px py. So these two get cancelled. So it's log 1, which is 0. So So the mutual information is equal to 0. But what about the conditional entropy? So it is xy. It's p of xy, which is px py log 1 over px given y. But what is p of x given y equal to?
P of x.
Correct, it's p of x, right? So this is simply sum over all x. You can just take y out and marginalize over this. You get p of x log 1 over p of x, which is equal to the entropy, right? So putting it back into this, again, you get that the mutual information is 0. So these are two extremes, right? So if x is equal to y, then the mutual information is maximized, whereas the conditional entropy is small. But if x and y are independent, then the mutual information is equal to 0, but the conditional entropy is large. It's equal to h of x. If you choose any other so if you choose any other distribution, then the mutual information will be in between 0 and h of x, and the conditional entropy will also be between 0 and x. So if you have h of x and I of xy, then the maximum value, I mean, we will formally prove this later, but the maximum value that the mutual information can take is equal to h of x. The maximum value of h of x given y is also equal to h of x. When I of xy equal to 0, h of x given y is equal to h of x. When h of x given y equal to 0, I of xy is equal to h of x. And anywhere in between, you get sort of a linear relationship between the two. So take any other distribution such that x and y are correlated with each other, but one doesn't give you the exact value of the other, then both the entropy and the mutual information will lie somewhere in between.
Yes, sir, it is clear now.
Okay, great. Any other questions? Okay, so if there's nothing else, then we can end the meeting for today. We'll meet again on Wednesday.